That's where your thinking's a little bit weaker than it should be. On the first one, I see 2 carbonyls. None of them are conjugated, so I don't have to worry about Michael. I see a strong nucleophile. So the first thing I think about doing is attacking those carbonyls with my nucleophiles, and I get hydrates of either one, so that's not the way to go. So then I go to plan B, which is the alpha hydrogen. The molecule on the left does not have an alpha hydrogen, the molecule on the right does. This is the classic situation where you make the enolate on the ring substance and attack the one that does not have the alpha hydrogen. This is an aldol condensation. Number 2, I have an ester with the matching base. So attacking it to enolate is not going to, or attacking it to carbonyl is not going to give me. So I must be making an enolate here. So I'm making an ester enolate, and it's followed up by acid. This first step is the glycine condensation. When I say glycine condensation, what's the most obvious thing that's going to follow? Saponification and decarboxylation. But I look at the next one, it's got the base. I like that. But it doesn't have acid and heat. What's it doing? It's doing an SN2 reaction. That's the alternative. Remember, at the end of class, we said when you finish up the glycine, you can either saponify and decarboxylate, or you could do 1 SN2, saponify and decarboxylate, or you could do 2 SN2 reactions, saponify and decarboxylate. Those are your 3 options. This one is to do 1 SN2 reaction, and that gives you B. And you look at what B reacts with. B is saponification. What is C? Right, and C has a carbonate, the C double bond O minus. The structure for C has the O minus on it because the acid was written out as a separate step. Then you decarboxylate. Number 3. Number 3 is a ketone, weak nucleophile, but it's a secondary nucleophile, so I know I'm making an enamine. Lots of questions about which side enamine goes to. It makes the less stable alkene, and the reason is the resonance structure. Sorry. My carbon. Sorry. Sorry. That was a little shocking there. Okay. The resonance structure for this delightful substance is push the negative charge into this position. And it is better to have the negative charge out here with fewer substituents than it is to have it on the inside. So when you make the enamine, you make what we call the anti-site alkenes, also called the Hoffman alkene, but the not stable one is the one you're thinking about. Okay? So we do that, and then this is the position that gets alkylated. And what does the acid do at the end? Right, so this goes back to being yellow. Correct. Enamine is almost always being produced in order to alkylate, and then you get rid of the nitrogen. Expect it, because that's the way it goes. Garrett. Sorry, Garrett.
Is the B product, would that be the stable form of it and not the ion of it? Because it can come back down and form a double bond again?
Actually, the product B would be this form with the nitrogen there, a positive charge.
You could drop that double bond down.
To the other side, no. It is the charged form. Okay, number 4 is acetoacetic ester. You know the structure. Okay? So we have the base. The base matches the carbonyl, or the ester, so I know I'm not going to do a whisk. I'm going to pull off an alpha hydrogen. It's a great alpha hydrogen. I'm going to do an SN2 reaction in step 2, followed by saponification and decarboxylation. How many people got that? That's exactly what you should expect. Number 5, I see a conjugated alkene. So the first thing that's going off is Michael addition. Do I have an enolate? Well, look at my recipe. I have a base, an ester, and some ethanol thrown in there. Could the base and the ethanol react together and make an ester enolate? You betcha. The enolate for Michael addition does not have to come from aldehyde. And so my ester enolate sitting here. Do exactly what you'd anticipate. And you close it down and you get a delta dicarbonyl. It doesn't say what kind of carbonyl it is, it's just carbonyl. Yes, your carbonyls or aldehyde carbonyls. How'd you guys do on that one? Number 6. I see a carbonyl, but I notice there are a lot of carbonyls or an anhydride, you only see the carbonyls. So then you look at your nitrogens. Hopefully at some point you would recognize that you have symmetrical or asymmetrical carbonyls. You have two different products. You have two different products. You could push off one side. This. Or you could get this. How many people got two products out of that? Thank you. How many people got one product out of that? How many people had no idea what it did?
In the mechanism, in the notes,
Yes.
it says that you have to protonate the anhydride oxygen
Yes.
before it can leave.
Yes.
Okay. Why is that?
So, because you're in a positive environment, and if it leaves as a negative thing, it's not so good.
Okay.
Now, honestly, sometimes the leaving group is so strong that it will come flying off as a negative thing and instantly pick up a proton. I think there is just semantics. Does it pick up the proton before it comes off, or as soon as it comes off, it picks up the proton?
Okay.
It certainly can do that.
Of the two products formed, the terminal, the one from the terminal carbonyl would be the more stable product, correct? That's because it's slightly more activated than the internal carbonyl?
Probably not enough difference to say it doesn't matter. I really don't think either side is going to be more reactive. I think you're real close to 50-50 there.
I have a question about the number of things about the phosphate.
Okay.
When there's a benzene ring with it, does that make a difference?
No, because you cannot break into the conjugated system with the air nitrogen. It's got to circle up and protect it. Okay. All right, number 7. Lots of questions about number 7. So let's take that one from the top. I say carbonyls. Are there any leaving groups? No. Strong or weak nucleophile? Weak nucleophile. Do I have the acid being sexy? Okay. So I've got a sexy carbonyl. What kind of nitrogen? Primary. So what products do I make with primary amines? Imines. Is there any reason to think that only one will react when I even wrote excess there? No. We're going to get double imines if you're writing the mechanism. One would turn into an imine and the other one would. It's not going to happen simultaneously in plus sites. For some reason I got asked that a lot. There were no mechanism questions, but I saw lots of people using mini mechanisms. Bravo, you get the right product. Number 8, also lots of questions, so let's take it from the top. Do you see carbonyl? Check. Is it conjugated? No. So don't worry about Michael. Strong or weak nucleophiles? Wait, I don't see water. It's implied though, isn't it, when you say dilute acid? What are we diluted with? Water. So there's dilute acid in there. Don't fall for that trick. So we got water in there. Tactic carbonyl, alpha carbonyl, stop getting a hydrate. What are you going to do? This is not the major reaction. If there was nothing else in the ring, if there was not an OH over there, this would be a no reaction, or you could write the hydrate and show that as the unfavorable equilibrium if you wanted to. But you have a second nucleophile there. So that's the other thing to consider when, it keeps seeming to give you hydrates or no reactions. Have you overlooked a nucleophile? Well, I look over here and I see a pretty good nucleophile in an internal acetal. So it makes a ring. How do we do? Alright, very, very, very good. How many people spontaneously saw internal? How many people used the flow chart thinking to kind of get them in that direction? How many people got that one just wrong? Okay, that's an honest group. Thank you very much. Number 9 on the flip side, because if the first 8 weren't fun, we got another whole back side. I've got an ester. Love the esters because you know they're going to do something. Highly unlikely it's going to be a no reaction. So it's going to whoosh. It's the number one thing I would think about here. I go over and I look at, I've got a nucleophile. It's the organolithium, and it's a really strong nucleophile, so I don't have to do any sexy carbonyls. I'm going to start attacking. Attack the carbon, open the carbon, close the carbon, whoosh. So, we have created at this point. Are we done? No. Because I have a carbonyl with no leaving group. Now I can't whoosh, but I still have a very strong nucleophile here, which is going to do this and open. We add this, and we're sitting here looking for a proton. Where do we get the proton from? Step 2.